Welcome to the Mega Motion Physics Poster. And the very first question is a momentum problem. It's the momentum of the pellet being transferred to the ball. Now the question is how fast is the bowling ball going to roll at the start? So you have to work out the momentum of the pellet. That will equal the momentum of the ball. You will need to use the gamma factor to work out and to adjust the mass of the bullet, because it is travelling at 0.99999 c. Finding the momentum of the bullet will give you the momentum of the bowling ball, and because you have the mass of the bowling ball, it's easy to find the speed. Once the ball is in motion, it's going to accelerate down this slope. And question 2 is, what is going to be the final speed at the bottom of the ramp? Now, you've got a few things. You've got acceleration, you've got initial speed, and you've also got distance of 10 meters. So you should be able to find what v is, v being the final velocity. Now the next question is question 3, find the angle of the ramp. Now it is the angle of the ramp that's created the imbalance which has caused the acceleration. So we'll just do a forces diagram, work out what the angle is. Okay, there's our weight force. We've also got the normal pushing the ball back. Now it's these two forces that create the acceleration, and the resultant vector is this green line right here, and this is the sum of all forces. This is the force that creates the acceleration of 1 meter per second for that 1 kilogram ball. Now if you actually work out the force, it's ma, mass times acceleration, and you get 1 times 1, which is 1 newton of force, and the weight force is 1 times 10 meters per second, because that's the acceleration of gravity. Now what you have to do now is work out the angle. You've got the sum of all forces, which is opposite the angle, and you've got the hypotenuse is your weight force, which is 10. So you can work out whether it's sine, cos, or tan yourself there. Question 4 is find the horizontal speed of the ball through the air. Now, when the ball did get to the end of that ramp, it hit a little flat section there, as you can see. Now that projected the ball out horizontally, so the speed of the ball should be through the air should be the same as the speed of the ball at the end of the ramp. Next question, what is the distance travelled along the ground below of the projectile? Now we know that the horizontal speed is always constant, and if we can find the time in the air and then we multiply the speed by the time, we should be able to find the distance along the ground. If you just drop the ball straight down, that time would be the same time as the path that's on the poster. So just work on the vertical components and you should be able to find the time that's in the air. The next question is, what is the speed of the ball impacting with the spring down below? Now there are two speeds you need to put together. That is the horizontal speed, which we already have. You have to solve the final vertical speed, and you can do that by using the formula v squared equals u squared plus 2ad to find the final speed. And then once you've got those two values, you then find the missing side, which is the hypotenuse. And you can do that by using the formula a squared plus b squared equals c squared. Okay, to find the angle of the collision with the spring, to go back to your original triangle, you've got 3 different side lengths, sine, cos, or tan. You should be able to work out what that internal angle is. The next question is find the stiffness of the spring. Now the kinetic energy of that ball has squashed that spring 10 centimeters, and all of that energy of the kinetic energy has presumably being transferred into elastic potential energy inside the spring. So the two values of energy are the same. So all you need to do is substitute those values of energy and also the 10 centimeters into the equation, but just change the 10 centimeters to meters, and you should be able to find out what K is just by rearranging the equation. Okay, the spring has released the ball into the air and it's moving up vertically and will eventually hit the green tin roof. Now the next question is what is the impact speed with the green tin roof? Now we are working with momentum here, because what we've got is we've got an impulse figure of 10 units. Now the ball presumably will stop dead once it makes contact with the roof, so our final momentum will be 0, and the initial momentum just before the roof would be equal to an impulse of 10. Next question is to find the height of the roof. Now this is a straight line question. What you need to do is you need to find what the initial speed is of the ball off the spring, and that should equal the speed of impact with that spring in the first place, because its original kinetic energy was stored as elastic potential energy, and on release the kinetic energy had been released into the ball. Now this ball is launched vertically and it will move up and actually hit the roof. Its acceleration is -10, and the final speed is when it hit the roof, and we've worked it out on the previous question with momentum. Here's a diagram just here showing you of the path of the ball, and we'll just write down some values. We know what A is. We have already found the initial speed of the ball off the spring, and so we're looking for D. D is the height. Our next question is, what is the speed of the ball at the end of the pipe? Now, as gravitational energy does get converted to kinetic energy at the bottom, that's the best way to find out what the actual speed is. Now, for the speed of the top of the loop, as it climbs up to the top of the loop, it's gained some gravitational potential energy, but has lost some kinetic energy, so the ball will slow down. And using those two formula, you should be able to find out what the speed is at the top of the loop. Question 13, will the ball have enough speed to make the loop? Just get your cheat sheet out and write the formula √GR. That will solve that question. Right, the next question, what is the apparent weight of the ball upside down at the top of the loop? So what you need to do is, first of all, is consider the forces. Now we know the ball is actually moving in a circle, which means that the sum of all forces must be equal to the centripetal force. That's Fc. But there's also a weight force in red there, and we've also got a normal, that's the push-off from the surface on the ball, and it's this which determines the apparent weight of the ball. That's the blue arrow, the normal. This gives us our apparent weight. Now, the sum of all forces is equal to the centripetal force, and that equals N plus W. Now we just have to rearrange this equation to make N the subject, to find out what the apparent weight is at that speed through the loop. Question number 15, what is the speed of the ball at the apogee? Now the ball was launched from the loop on a 30-degree angle, so the horizontal speed would be cos 30 degrees times the actual speed at the bottom of the loop. So that would be the horizontal speed throughout the flight. Once the ball has made it to the top of the funnel, its horizontal speed is equal to its orbital speed, and the ball rotates around at the top, and it's the banking of the track, or the angle of the funnel wall, that keeps the the pressure on the ball to maintain its circular motion. Now here's our normal. This is our weight force, and the ball is moving towards the centre of its orbit. This is the centripetal force here in the pink arrow, and the angle of the track is equal to this angle up here. So let's just work out some formula. The sum of all forces is mv squared over r. We know what the speeds are, the radius and the mass of the ball are. Opposite the angle, and the weight force, of course, is adjacent to the angle. So this is a tan figure. It's equal to the centripetal force over the weight force. Now you can substitute the values of those equations into that green equation, and you'll end up cancelling, and it comes up with a fantastic formula that you can put down on your cheat sheet. I mean, you can do a problem like this, but this is the summary of it. Tan angle of the track is equal to v squared over gr. That's the quickest way of doing the problem. Now when the ball pops out of the funnel, it moves down this 30-degree slope at a constant speed. Now because it's travelling at a constant speed, the acceleration is 0, which means that that the forces are balanced. When you do get an acceleration, it means that the forces are unbalanced. So we've just drawn in a weight force and a normal for the ball, and this would be, in the pink, this would be our sum of all forces, but it's not. It's the resultant vector of those two vectors there, n and w. There's our 30-degree slope, and this resultant vector must equal to the frictional forces. These two vectors must be of the same magnitude and cancel out because they are in fact going in the direct opposite directions. So find R and you'll have your frictional forces. To answer the final question, how high the ball gets, we need to first of all find out what the speed of the ball is off the piston. Now the initial speed of the ball was 0, and the impulse is F times t, and the two values are that being given on the piston. That also equals the change of momentum, mv minus mu. Now the mu was 0 because the ball was just resting on the piston at the start. So you've got all those values, you just rearrange the equation to make v the subject, and you'll find your initial speed off the piston. Further on, how high did it go? You're talking about an acceleration of minus 10. We know what the initial speed is from the previous calculation. We have to find we know that the final speed is 0. We have to find the distance that travels in the air, and use v squared equals u squared plus 2ad. That's the best one. Rearrange the formula to make d the subject. And that is the end of this exercise. I hope you've had fun doing it.
Now listen to what I said. In your life expect some trouble. When you worry you make it double. But don't worry,